Hello, my name is Gabriela, and today I'm going to do the phase C1 from the hydration monitoring wristband. This is the last phase for the capstone one, and it is individual, so it's only me in this presentation, and also the professor, the engineering Alex Velez Cruz. Now I'm going to have the outline. We're going to talk about the interface diagram, the detailed analysis, and design studies for the system level and also for the critical components. We're also going to talk about the design to specifications and drawing. Um, in that section, we're going to talk about the battery size and its performance requirements, and also the technical notes for the engineerings. And we also going to talk about the verification, detailed breakdown from critical components, and the project plan. Last one, it will be the budget tracking versus the original. Now in here, we're going to have the interface diagram. We're going to start with the external power source. Then you're going to break down through the power and energy management, regulates power for all subsystem. And then we're going to have that divided into two, the energy status and the energy usage. The energy status, we're going to have the sweat sensor system, measures sweats and electrolytes level, and it's going to do a power demand. So we're going to find the battery energy storage and also the environmental conditions like temperature and humidity. From the energy usage, we're going to have the data processing and analytics system. That's going to break down into a power demand that is going to talk about the power, the mobile app communication, and also the thermal conditions. In here, we have the detail analysis, design studies, the energy consumption analysis for the low power wireless system design. For the microcontrollers, select based on the power consumption in active and idle states to optimize efficiency during logic communication task. From the Bluetooth, the BLE, we have chosen for its minimal power usage in active transmission. The low power sensors, hydration sensors activate immediately, reducing overall power consumptions when idle. And the goal is to integrate low power components for minimal energy consumptions without compromising functionality. From the battery and charging analyzed for low power system, we have the battery selection is going to be 500 LiPo rechargeable battery chosen for its compact size, high energy density, and sustainable for wearable. The battery life systems consume 100 during active data collection and 10 during idle. Charging time battery can fully charge in under 3 hours with a 200 milliamp charging current. And also the goal is to optimize battery life and charging efficiency for continuous operation and quick recharging. From the approximate analytics calculation, battery life calculation, we expect average power consumption is going to be 90. The battery capacity is going to be 500. The estimated battery life is going to be 20.5 hours is the basic estimate. And we have a note that is the low power modes during idle will ensure the system meets the 72 hours target. The charging time calculations, charging current, it's going to be 200 milliamps. And then the charging time is going to be 2.5 hours within the 3 hours requirement. The goal is to confirm battery life and charging times are optimized for system performance and efficiency. In our right side, we're going to see the MOP compliance. We have the MOPs, the target value, and the achieved value. The MOPs are the energy consumption, battery duration, active power consumption, idle power consumption, charging time, charging voltage, and battery health monitoring. From the targets, we have them in here, and if we compare them with the achieved values, we see that the values are achieved. The detailed analysis design studies for the critical components, the energy storage system, it means the LiPo battery, it's going to be materials. LiPo battery offers high energy density and design flexibility for compact wearable. Manufacturing constant shape LiPo batteries with sealed packing ensures safety and efficiency. And also the battery capacity requires 1.8 for 72 hours operation. From the PMIC, the materials high efficiency semiconductors and thermal management materials. The manufacturing small form factors PMIC with flip chip or wire bonding, and also the efficiency or the PMIC with more than 90% efficiency ensures minimal power loss and maximize battery life. The wireless communication, that it will be the BLE, the materials low power semiconductors for efficient data transmission. The manufacturing surface mount technology, SMT, for integrations and reliable antenna placement and energy consumption. BLE typically consumes 10 with periodic transmission. The range is efficient range 50 meters affected by environmental interference. Now we have the MOPS compliance verification with charge. The components are energy density, cycle life, charge time, thermal performance, battery capacity, power efficiency, current protection, power consumption. And now we have the MOP, the LiPo battery, the supercapacitor, and all of them. The design to specifications and drawings. The battery design specifications for low power wristbands. The key requirements: battery capacity from 500 to 600. The thickness must fit within the wristband thicknesses. And then form factor thin rectangular LiPo battery to align with wristband design. Battery dimensions is going to be the length 32, the width 20, and the height 2.5. The LiPo battery specifications: nominal voltage 3.7 voltage, charge voltage 4.2, discharge voltage 3.0, max charging current 215 between 215 and 300, and the max discharging current is going to be between 500 and 600. Temperature range is going to be, charge is going to be between 0 Celsius to 45 Celsius, and the discharge is going to be between negative 20 Celsius to 60 Celsius. We have the battery. It's going to be, as we mentioned, the length of 32 and then the width of 20. In here we have that the rounded is going to be 1.0. We have, again, the 32 length. We have the 20 width, and we also have the thickness of 2.50. Here we have the design in another parameter. Then we have another design. This is a battery. This is adhesive. This is a double adhesive. This is a PMC. And then from the battery science and its performance requirement, we have the components, we have the dimensions, and we have the notes. For example, component LiPo battery, the LP503759. The length should be 32, the width 20, and the height 2.5. And then in the notes, I write down compact wearable size. For the power management circuit, the length is going to be 10, width 10, and height 2. And then typical size for most wearable application. And all of them are written down in here. The design to specifications and drawing. Technical notes for battery integration and wire routing. We have LiPo battery. These technical notes are the ones that we are going to send with the designs for the engineering. So we have the first note will be the LiPo battery placements and integration, the battery size, align along wristband length, and then position and ensure optimal space utilizations and airflow to prevent overheating. Securing, use Kapton adhesive tape for insulation and secure placement. And then we have the wire routing and protection. We have routing planned for red, positive, and black negative wires to avoid strains and short circuits. Secure and use double-sided 3 adhesive tapes to secure wires within casing. Protections protects wires with Kapton tape to guard against damage from sweat or external impact. Goals: ensure safe and efficiency battery integration while protecting wires and components. Here we have the verification. We have the component, the MOPS, the target value, the achieved value, and the compliance. As we can see, all of them were met requirement. Also, we have the detailed breakdown for critical components. And we also have the component, the MOPS, the target value, and the achieved value. And we can see that some of them requires monitoring, but also some of them were met. So here we have the verification still. We have all of the breakdown that we already talk about it. Also, we have the project plan tracking. If we can see the development phase C1 presentation, it was in the third and the fourth month of the trimester. And then we also are going to wait for the development phase C2 presentation that it's going to be on the third week of March. We have the budget tracking. It is the cost versus the original estimate. Total cost for this side, it was 45 with 75 per unit. And then the total for 1,000 units, it was 457 with 500. The original was 7 per unit. And then for the total of 1,000 with $700. Comparison and conclusion over budget. Estimated cost per unit was $45.75. It is significantly higher than the original budget that it was $7. Action needed to meet the budget considering reduction components cost or relocating found from other areas. Thank you so much. And that's it.